Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening to wherever you are. Welcome and thank you for joining our latest AI for Good climate science session. I'm delighted to introduce Ashish Chakrabarty, who's an assistant professor in applied maths at UC Santa Cruz. So Ashish did his PhD at Rice University, but previously to that was also a research scientist at Xerox, Palo Alto, and SRI. And has done a lot of really interesting work on theoretical aspects of deep learning around how neural networks learn what they learn, and also its applications in computational physics, and has recently been applying that to climate modeling and climate emulation. And I'm really excited to hear about the latest aspects of his work. So without further ado, thank you very much, Ashish, over to you.
Thank you so much for the kind introduction, Duncan. Okay. So today I'm going to talk about AI-based autoregressive models of our coupled climate system. This work is done in collaboration with a bunch of folks, and different aspects of it would be highlighted. I wanted to highlight the graduate students who are involved in this particular set of work. Hyman from Penn State, who co-developed Lucy, which I would talk about, then Conrad, who did some of the theoretical aspects of this work, and Moeen, some of the other stuff that I'll talk about during the course of this talk. Okay, so the main challenge in modeling the climate system, and this is irrespective of AI-based modeling or physics-based modeling, is the fact that it has physical processes that interact at multiple different scales. And the scales of these physical processes go from a few micrometers to several thousands of kilometers, and similarly in timescales, where it goes from seconds to essentially decades. And the key aspect of this multi-scale system is the fact that you cannot quite call off a line. You can't really call off one scale and say that you can separate the processes between large scales and small scales. So these are tightly coupled scales, and to be able to fully resolve the system, you'd have to resolve the entire set of spatiotemporal scales, which are inherently computationally intractable. So because of that, we often resort to approximation techniques even in physics-based models. The hope for AI, at least in the early ages of AI-based climate or AI-based weather, was that some of these approximations that are often ad hoc, empirical, but still grounded and inspired with physics, can be tackled with AI-based modeling. In the next few years or so, it turned out that AI-based emulators took a very different route, where the goal was to seamlessly model across these scales using fully data-driven architectures. An early example of that was FouRKS, which was a large collaboration between NVIDIA, Rice, Caltech, where what we essentially did was we took all the states of the atmosphere, about 33 variables of the atmosphere across different vertical levels, at the highest resolution observational weather data that we had, and fit a very big neural network. And as you see throughout the length of this talk, I wouldn't really be talking a whole lot about neural architectures, but instead, call them big models, and then try to do some theory where you wouldn't have to worry about the fact that what kind of a model it is. But generally, the idea here was that we take a large model, we train it on weather observations or observation-derived reanalysis products in a very simple setting where we show it the state of the atmosphere today and try to predict the state of the atmosphere the next day. And this could be today to next day, T to T plus 6 hours, T to T plus 12 hours, depending on what you want to do. And then just train the model like that. No physics, no physical constraints, no energy budget, no conservation laws, nothing really imposed. And it gave us very encouraging results. In fact, the results were were competitive with numerical IFS, which was sort of the state of the art, or which is still sort of the gold standard state of the art numerical weather prediction models. Since then, there have been a bunch of different AI-based weather models that have shown amazing accuracies and performances that are off the charts when compared to physics-based models, some of them being Pangu from Hawaii, GraphCast from Google DeepMind. ECMWF now has their own AI-based model, which outperforms their physics-based gold standard model. And this was all done simply by scaling large deep neural networks, keeping in mind that, again, there was really no physical constraint. So fully data-driven models was able to simulate this system across the scales, at least for weather timescales. And that's essentially where this talk starts, is that are there challenges when we take these AI-based weather models and then try to think about climate modeling, right? Climate modeling is weather modeling, sort of, and then you have to do this for longer time scales, and then there would be interactions with the oceans and the other parts of the Earth system, so there are those challenges as well. But at the very least, it requires you to take these AI-based models and be able to run them at much longer time scales, and that's one of the fundamental challenges with these models that we have sort of overcome, but the story is a little longer, so that's where we get into the depth of it. So these kinds of models that are unrolled in this fashion, where it takes the state today, predicts the state the next day, and then plugs that in and gets the state the day after, and so on and so forth, are called autoregressive models. And this is a very common architecture, right? This is the kind of architecture that is used in language models as well. And we all know what the challenges with language models. So let's think about what can be the challenges with modeling the climate with an architecture like this. The general approach to building these architectures involves replacing this right-hand side, right? So the climate system is basically a large set of equations that roughly look like this. For the purposes of this talk, it's not important what G is, except that it's some complicated nonlinear operator, or a combination of linear and nonlinear operator that sort of spans the whole stack of physics that contributes to the climate system. And the autoregressive model is trying to predict the next time step by approximating this integral, which is the state to date and state today plus the integral of the nonlinear operator. And this is typically done with very large deep neural network. The issue with and the way this is done in practice is that you start off with the random neural network. You send it, you show it states today. You predict something, and then you match it against the true state at the next day. And you do this over the 40 years of observational weather data that you have, hoping that you learn meaningful parameters theta, so that you can then run this model in inference for a long time, or for a short time, depending upon what your application is. The issue with modeling systems, modeling complex partial differential equations like the climate systems like this, is that the stack of work that comes out of this is that every time we have a new n, we have a bigger n, or some more layers, or this new magic sauce in the machine learning model, we are unable to explain what goes on there, right? So there were these convolutional models that were really popular, at least a while back, for weather modeling and then sort of climate modeling, and then transformers and neural operators. And then we often resort to the fact that when some of these things don't work, we kind of say that our data is unique, hence it doesn't work. And for the longest time, we used to believe that turbulence is almost impossible to model with machine learning, but clearly that was not the case. And then there are certain other difficulties that are much harder to reconcile with. For example, if you train a model with a larger delta t, it turns out that you get better performance from these models. But if you train it with a smaller delta t, it kind of deviates much more quickly, which kind of goes against our notion of how numerical analysis works, is that you get better performance out of a numerical model when you have a fine-grained resolution of your temporal steps. So so these are some of the issues that, and the first one is not so much of an issue as more of a philosophical problem that we can't explain what's going on, but we can still live with it if we can do great engineering. But the second one is more like a fundamental issue that doesn't quite make sense. So we wanted to investigate this in a previous paper a couple of years back, and we ran some of these early AI weather models. These are still state-of-the-art AI weather models for longer timescales. And we realized one of the two things happen: either these models blow up, which are the top models, and the other case is where it doesn't blow up and it kind of remains it's stable and shows you patterns of the atmosphere that looks reasonable. For the first case, we can clearly say that okay, there's some energy budget mismatch which was never there to begin with, so probably this doesn't work for climate timescales. That's all right. But the second set of models, which also didn't have energy constraints but still remain stable, are interesting, because when we look at some of their derived climatologies, we realize that these models are bounded in the sense that they're stable, but they produce incorrect climatology. So the way to read this graph is that the black line is sort of the mean Z500, or the mean pressure field 5 kilometers above the Earth's surface, mean geopotential fields 5 kilometers above the Earth's surface. And the colors around it are the different AI models that remained stable for 10 years, but they all kind of get the wrong mean. One could argue that, okay, maybe the mean is not too bad. There's something weird going on in the poles. But then if you look at the velocity, the zonal wind of these models, you would realize that, okay, something very wonky is going on, because you see wind velocities for some AI models being 20 meters per second near the equator, which is sort of a doomsday scenario. You shouldn't expect models to behave that way. So even if they're stable and bounded, they seem to produce unrealistic physical simulations, which is not surprising. They didn't have boundary conditions and didn't have energy constraints, but yet they remain bounded, right? So they didn't go unstable, they didn't blow up, which you typically expect to do. So something is going on there, and towards the end of this talk, it's probably in the last 30 or 20 minutes of this talk, I will try to explain to you what might be going on, or some early attempts of explaining what might be going on in this class of autoregressive models, not just for weather or climate, but for any system. So we started investigating this and thought maybe we could ask some basic questions that, okay, are there structures that we can put in N that fixes these problems, so that we can simulate the systems? Sure, but also something a little more profound, that can we build structures into N so that we can predict the behavior of N? And this is not something that scientific machine learning applications would often think about, is that we have a problem. The problem has several complexities. We want to build a model to solve this problem, right? So whatever little adjustments we make in these models, it's meant to solve a scientific problem. Here we want to do something slightly different. Sure, we want to solve the problem, but we also want to be able to say how this model would behave, right? So for example, if a model goes unstable, can we build structures around it so that we can guess whether this model would go unstable? If it's going to hallucinate like in the previous case, where it generates physical simulations, but they don't make sense, can we say something about that by investigating N? And by investigating N doesn't mean that we break open N and look at each layer and each neuron, because that might not be fundamentally the correct way of looking at things, but something around that. So this comes from this idea that whenever we were doing science for the longest time, we had this reductionist philosophy where you want to build theory, and then you do hierarchical modeling, but your theory has to be sort of constrained by the observations, right? Your theory has to reconcile with the observations, And that's how you're able to do hierarchical modeling. Right? These three things were very tightly coupled. The way we have always done machine learning for the physical sciences, including weather and climate, but also broadly, is that we have built models based on algorithmic intuition, and then we have directly jumped to the hierarchical modeling part, right? We believe that transformers make sense. We believe that neural operators make sense, not because there's a theory and a theorem that proves so, but because we feel like that should be the right way to do things. And then we directly move to applications and hierarchical modeling. And the hope is in between, we can distill a theory that looks more like the theory on the left-hand side, looks more like a scientific theory, and then see whether this theory scales when we go to really large and complex systems. In our case, the very large and complex system, the implementation at scale refers to like a full-blown climate model that we can build, that we can test, and see whether it does, whether it talks like a climate model, whether it walks like a climate model, and everything else that a climate scientist would expect from a model. So in the next few slides, what I'm going to do is first talk about the algorithmic intuition based on which we thought that there might be some issues with these weather models that we can fix, and then they could directly jump at this implementation at scale. The issue that we kind of converged down to was, or one of the many issues that might be there. Of course, there are some issues that we know right up front, that there's no budget, there's no energy constraint, there's no boundary conditions, so on. But even more so, a more fundamental issue that you have in these models are that while their predictions are very accurate for the first few days and weather timescales, if you look at their predictions in Fourier space, it seems that their wave number was the Fourier transforms, or the spectral energy content, is terribly off. And what do I mean by that is that if I look at the true observational zonal wind spectrum, which is given in black, and I look at all the other AI weather models at their day 10 prediction, keeping in mind some of these models do really well at day 10. So what you would notice is that only a few of these wave numbers are actually captured, which is about less than 1/4 of the wave numbers, and everything else is off. And at this point, one might be inclined to ask the question that, okay, maybe at day 10, you're losing out accuracy, and it's not something that you'd expect from a model. So if you look at things at the first time step of prediction, and to remember, it's critical to point out that these models were trained to predict a single time step, and then they're unrolled or autoregressively unrolled over 10 days. But if I look at the first time step of prediction on which you have written the loss function in your training process, you'd realize that only 1/4 of these wave numbers are captured. Everything else is off. So this kind of highlights a fundamental issue in training deep neural networks, not just for the physical sciences, but also for any other system. For some systems, it might matter. For some systems, it doesn't. Definitely for climate science, it does. You cannot capture the small scale processes of your underlying system. And we call this spectral bias. And the question was, is this a uniquely climate problem, like weather, turbulence, these kind of physics problem, or is this a machine learning problem? Now, to answer that, you have to do more than diagnosis. You now have to go back to the basics of a deep neural network and see whether you can derive or show that a problem like this exists. Now, for the next slide, if you're not a very math-savvy audience, you can ignore almost everything I say until I come to the very end of the slide. Hopefully, then it would be much clearer. The way we show this is that we take a single-layered neural network, and then we use something called the principle of mathematical induction to induce over multiple layers. The idea is I want to show that this problem is not a physics problem, it's an ML problem, that this problem would exist no matter what you train your machine learning model on. And the way to do that is that you write out the basic equations of a deep neural network with a single layer, and then you represent this equation in Fourier space. When you want to represent this equation in Fourier space, what happens is that these things like the nonlinear activation, the affine transformation, they undergo a change in space and yields very nasty looking mathematical quantities that for the longest time you can ignore. What you need to remember is the way these models are trained is that you're given a target function, like the state of the next day, and you try to match that target function. So how does that work? Your target function is this blue curve true, and your neural network's prediction is black. Okay, you basically have a blue spectrum and you're trying to match it with this black line. So that's the general idea. And what I'm going to show is that no matter how much you try, you would never be able to get the entire length of the spectrum because of certain properties of any deep neural network. And these properties emerges from the way we do optimization is that if you write your loss function and then you think about how is the neural network trained, it is trained by calculating the gradient of your loss function with respect to these parameters and then moving those gradients along that, moving these parameters along that direction of the gradient. What you'd realize are that the gradient terms are such that at the end of the day, you're going to see an expression that scales with the exponential of minus of the wave number, which basically means is that when you have captured the large scale processes of your system, when you have captured the large scales or the low wave numbers, your AK term is very small, and at the high wave number, your exponential minus K term is very small. So you essentially have two very small quantities that are multiplied with each other, and you can't move the loss function anymore. So you're stuck there. So you stay here with a bias. And the reason why this happens is because the spectrum, the Fourier spectrum of most of these variables that we encounter in climate modeling have this decaying nature, while as opposed to the spectrum of a cat, the image of a cat would be much more flatter. And those are much easier to capture because you don't have this decaying behavior, so AK doesn't become small very quickly. So this was sort of the fundamental bias that was causing this issue. And once you have a bias like this at the first time step, if you unroll this model for a long time, this bias is going to slowly grow up into the large scales and either make your model very unstable. And if the bias is in the other direction, it's below the blue line, it's going to diffuse down and generate a saturated atmosphere, as was the case in many of the early AI weather models. Now, to fix this problem, we decided to do something very simple. We decided to do what most climate scientists would do: is we train this model like a residual model. So instead of predicting the entire right-hand side with a large model, we predict only the derivative with this large neural network. Again, it doesn't really matter what this neural network is, as long as it's sufficiently large, trained on a lot of data, they all seem to do pretty well. And then you write out this integration as an explicit smoothing kernel, which is basically what we all learned in numerical analysis, where we were routinely doing ODE integrations. And this is not a new way to train models. People have been training models like this for a very long time. They may not have been training it with an RK4 type smoothing kernel, but this, for example, is very similar to a ResNet or training on residues and have been done in the past. What we would show is that, first of all, this algorithmic intuition, this is not a theory. There is no rigor here. There is no reason to think that this is more mathematically accurate than predicting the entire right-hand side with a big neural network. But at the first step, we would show that this algorithmic intuition will result in a climate model, would result in us building a climate model that remains stable and has the right sort of budgets and constraints as we unroll into a very long time. It's important to note that, and we would show that towards the end of this talk, is like even if you do not have these constraints, there can be instances when your model would still be stable. And to be able to answer these questions, whether or not you could be lucky enough to be stable, or you could control the amount of stability you have in these models, are something that we would distill out as a theory. So that's why I said we wanted to build these principal structures, not only to fix our problem, but also to be able to say whether, given a large neural network trained like this, we can guess, we can take an educated guess as to how this model would behave at longer timescales, shorter timescales, or medium range timescales. The other thing that we did was we fixed spectral bias by having a spectral regularizer in Fourier space, wherein the small scales that we were missing out is basically now captured back is basically now captured back with an extra penalty term. This is sort of the dirtiest way of fixing spectral bias. I feel that there are many other different ways you can fix spectral bias. I also feel that there is no solution that would ever be exact for a decaying spectrum in a large-scale system. But anyway, we put these two things together and we started building models at scale. So what we would do is, in that little cartoon about algorithmic intuition, hierarchical modeling, and implementation at scale, we're looking right now at the implementation at scale part of it, where we took, again, all sort of observation derived reanalysis data, coarse resolution in this case, and there are consequences of that, but not very important for this talk. But coarse resolution on 300 kilometers. We took the CO2 forcing and we embedded it into the model. We also have a short circuit path where you can prescribe SSTs, which are the boundary conditions to this model, and then train a model exactly with these two principal structures. One is an integration constraint, and the other is a spectral regularizer. So this integration constraint could be Euler, RK4, any of your favorite smoothing kernels, and the spectral correction in this case is done not on the state but on the tendency of this model, along with a regular MSC loss, which is done in spherical harmonics. And then we let this model train this model for a few years. We can train one of the important aspects of presenting this work is that Lucy is an open source model which is extremely lightweight, and the lightweight part comes from a lot of engineering efforts on our end to make it sort of a place to do sandbox experiments. So you can train Lucy with as less as 2 years of data. You need 2 years to get the cycle of temperature. But you can train it as less as 2 years of data, and because it's coarse resolution, you can actually run it on your own laptop and do sort of what-if experiments with it. The 3D version of this model, which I'll talk about here, is much more expensive because it has all the levels of the atmosphere, and it's trained still on 10 years of data. It's actually not trained on 40 years of data. There is not a huge difference in the performance that we obtain from Lucy because of this reduction in training data. Of course, there are differences. But the reason is, like, we wanted to build something that was sort of more academically accessible, where you could do sort of sandbox type experiments, try things out more than presenting this as sort of like an operational AI-based climate emulator. But in the next few slides, I'll try to convince you that it does walk like a climate model, it does talk like a climate model, but there are probably 100 more steps before we can actually call this a real climate model. You could do large ensembles with Lucy because it's very cheap to run, so on and so forth. So this is, for example, Lucy's sort of 100-year climatologies with current CO2. So we're not increasing CO2 or that. So this is more like our controlled climate in this case. Lucy's and for era 5 we look at 10-year averages. And this is also averaged over 100 ensemble members as well. The climatologies actually look pretty neat. We also compare it with a very traditional type SPD model, very simple climate model. We look at the biases in both temperature, zonal wind, humidity, precipitation. Lucy does have a dry bias in precipitation, which I guess might be the case for other AI-based climate emulators as well, but this is something that we notice in Lucy. It's much more pronounced in the 2D version as it is in the 3D version. The other important thing that we wanted to point out was sort of a benchmark, or like one of the important benchmarks that a climate model should pass is its ability to resolve the space-time, the spatial and temporal frequency chart of some of the important waves, some of the important large-scale waves in the atmosphere. For example, the Madden-Julian oscillation, the large Kelvin waves, and the AR waves. Lucy does get a lot of it. This is at a course of this is 300 kilometers, while most of the traditional climate models are at 100 kilometers, but we still sort of get the right signal in this Wheeler, we call it the Wheeler-Colitis diagram. We get some essence of the MJO as well, and we sort of get the Kelvin waves correctly as well. So that's one of the other tests that we wanted to do with Lucy to check whether it behaves accurately as a climate model. We look at variability in Lucy for the largest time in our hierarchical modeling. We had a hard time capturing variability in these models. So climatology is first order movement in these systems. Variability is analogous to second order ones. These are also traditionally called EOFs in climate science. We look at the southern and the northern annular mode, which are persistent, which are patterns that persist over long periods of time in the atmosphere. We see that both the northern and the southern hemisphere annular modes are roughly captured by Lucy. The structure is roughly captured. There's some question about the amplitude, but overall it gets the second order structures correctly. The average annual temperature range is another variability you'd expect in a climate model that roughly corresponds correctly between the observations. There are 5 other observations, in this case observation derived reanalysis as compared to Lucy. Then the next bit of test would be focused on extreme events. And in a previous paper, one of the things we pointed out was that if you look at some of these AI weather models which we wanted to do, so for example, predict the track of tropical cyclones, and it does an amazing job at that. In fact, one of the very key contributions to the GraphCast and the Pangu paper, and even the FouRKS paper, was that it was able to capture the track of category 5 storms more accurately than physics-based models. It turns out that while it does such a good job in capturing the tracks, it doesn't quite do a very good job in capturing the intensity. So it doesn't get the intensity correctly of tropical cyclones. In this particular paper, what we wanted to show was if you do not see certain extreme events in your training data set, those events are called gray swan events. These are events that are possible, that are physically possible and will probably happen, but you do not capture them in your observational records. So if you have events like that, these gray swan events, you would never be able to capture them during inference with your AI weather models. And the reason comes from a variety of different things, and you can read the paper for those details. But mostly because you don't have stability, you don't have the right physical consistency, and so on and so forth. So we wanted to focus on whether or not we are accurately capturing the extreme events. That's a more difficult question for a climate model, but whether we can even extrapolate beyond the training set. So what these plots show are the return periods of extreme temperature zone winds. The key thing to note here is that it's trained on 10 years of data, and then it's emulated for 100 years. Ideally, if you did this with an AI weather model, you would never be able to get an event. For example, 10 years of era 5 has 310 Kelvin as the largest temperature it has ever seen. If you run an AI weather model, you would never be able to get a temperature field that is beyond 310 Kelvin. That's what the PNS paper previously showed. With Lucy, you were at least able to extrapolate beyond it. You were able to generate extreme events that you have not seen in the training set. This, of course, does not guarantee that this extreme event over here, for example, is a correct one, or even a physically consistent one. That requires a lot more analysis and effort on our part, and we're doing that. But at the very least, if you are able to unroll these models for more years, you would be able to capture gray swans. That was the hope of AI emulation in the first place, that if you can unroll these models for a very long time, over many ensembles, then you should be able to estimate the statistics of extremes that are not there in your training set. And this is sort of validation of that hope that, yeah, you can at least capture some of these events. You can at least generate some of these events. Whether or not they're accurate is a separate story. And is not part of this presentation. The next set of experiments are with a change in carbon dioxide. So first of all, we wanted to see whether we do get the non-stationary surface temperature change with Lucy, and whether it also responds correctly when I turn off CO2. For example, by turning off CO2 means that I take 1981 CO2 and hold it constant. If I do that, then I should not see an increase in the temperature trend. This is the global mean temperature. These are given by sort of the horizontal lines where I hold the CO2 constant, which means it's responding correctly to that. And then if I don't hold it constant, if I let it evolve with the observed CO2, it gets the slope correctly. And there are two of them. One of them is with SST, one of them is without. They're roughly the same, matches with the of 5. And this is not such a hard, turned out this is not such a hard problem as long as you're able to embed CO2. This is still with the observed CO2 though. You have not really increased the CO2 levels. You're not exploring what if scenarios, which is sort of the next plot. Keeping in mind, this is the surface trend of the observed CO2. You get the trend correctly. And these are sort of the surface temperature PDFs when you are now going to unknown scenarios where you keep increasing the CO2 content in your atmosphere. And LOC seems to respond the way you'd expect it to. Hotter becomes hotter, colder becomes colder. More the CO2, the more extreme temperature events you see, more heat waves that you expect. This is still the global PDF. What happens at regional scales, I guess, is more interesting for a model like this. Then you look at the non-stationary climate structure, the vertical structure of the non-stationary climate, and you see that there are still many issues with these emulators. To begin with, the specific humidity structure vertically is not that accurate. The other major problem is the stratosphere, which I guess is a problem for a lot of these emulators, but is that you see an unreasonably cold sort of stratosphere, which we will see in a couple of more slides as well. But generally, when you're far away from the stratosphere, you actually do get the change in the vertical structure accurately, but you really mess up the stratosphere both for temperature and for zonal wind. I'd quickly show you some AMIP style experiments where we do plus 4K, plus 2K sort of SST biased experiments where you heat up the ocean by 2 Kelvin and 4 Kelvin and see what the responses are. The responses are not too bad in this case. We do see something that we expect. We don't see it to the same order as we would expect, but there are no unphysical cooling over land, which is sometimes an issue, and the way we fix that is by smudging the SSTs when we imposed it smudging the bias when we imposed it onto the SSTs. The key takeaway from this slide is that you can do climate change experiments by adding a bias to your SSTs, and you get a reasonable response. This is the time series corresponding to the time series corresponding to the temperature, surface temperature over land when you increase the ocean by 1 Kelvin, 2 Kelvin, 4 Kelvin, and this is the PDF of the temperatures where you see a systematic shift onto the right. Now, exactly how accurate these responses are as compared to a climate model is still something that we are analyzing, we are looking at, and this is not the end of the story. By that I mean that that while the general trend of how the temperature responses look like is correct, it doesn't mean that the exact values are correct. Also, there's no verification for climate change simulations except for global climate models. So that's a different challenge as well. The main drawbacks, as I can see, is how the stratosphere responds in these climate emulators, and could be a variety of different reasons. The stratospheric cooling trend is not correctly captured in Lucy. However, if I initialize a model from 1980s and I let it run, it seems to capture some of the dynamics pretty accurately. For example, we were tracking a single sudden stratospheric warming event. If you're not a climate scientist, this is basically the polar vortex breaking and making Chicago unbearable and things like that. So a sudden stratospheric warming event, and while it has a small time delay between when it captures it, but the overall pattern looks pretty accurate. The reversal of the wind because of the change in the temperature is pretty accurately nailed down by Lucy, even though you initialize it at 1980s and you let this emulation go over 20 years. I think this is an event that we look at 2013. So that's roughly after 33 years of emulation with Lucy. So it does get some essence of the stratospheric dynamics correctly, but then at the same time, it doesn't get things like the frequency of QBO and other more physics-based metrics that you typically look at. You can spin up Lucy from a 0 atmosphere and climatology, and it would convert to the right climate. You can control the CO2 when you spin this up. So for example, you can spin it up with a constant CO2, and you'd see that it settle at a lower sort of temperature value. You can spin it up with the currents, with the actual CO2, and you'd go to a larger value. So this gives us an impression that perhaps we should start thinking about whether we can do sort of paleo reconstruction experiments with models like this. At least this is hope that some of those experiments can be done with Lucy, and we're thinking about them as well. Now, this was the implementation at scale part of it. So it seems like these two little tricks sort of works along with maybe a bunch of other engineering tricks. What we want to do, and I'm a bit over time, but what I want to do maybe in the next 10 or 15 minutes is I will try to distill a theory out of what I just discussed, that there are these two principal structures that I used to stabilize the model. Maybe they played a part, maybe they didn't. If they did, how do they actually play a part, and can we build theory the same way a scientific theory is built? So that's the general idea. And let's remember what we did. Instead of replacing this right hand side with a large neural network, what we did was we predicted the tendency, and we put a smoothing kernel in the form of a time integrator inside this neural architecture. So these are differentiable blocks through which we can take gradients and so on. If you think about this structure, and if you're a numerical analyst, you can think of doing something a little more fancy, which is done in more computationally advanced PDE solvers, that you can do things like implicit numerical integration. You can try to solve this system using deep equilibrium models, where you find a more accurate representation of xt plus delta t by solving this as an implicit system and with a linear solver. So you can extend this idea of putting an integration scheme in the same way you think about doing numerical integrations of PDEs. Now, what does that enable? It enables us to do linear stability analysis. Linear stability analysis is a method by which we take a solver, we take a model, mostly a black box model, compute a diagnostic metric without always looking into the system with a microscope. And based on the metric, we're able to say how this model is going to behave. How is this error going to grow? And more importantly, given two models, we should be able to distinguish which model will become worse more quickly, or which model will go unstable more quickly, or if there are other idiosyncrasies of this model that would kind of get revealed through an analysis like this. So linear stability analysis takes the true system, takes the predicted system, and tries to compute the error. And the next few slides are a bit math heavy, and I will not go over them too slowly, but I'll try to point out how, where the important parts are. So you compute the error between these two models, and you can't really do anything with it. You can't really chew on this expression. You don't know what this is. This is a giant neural network. You don't know what this is. This is the true system with unknown physics. So instead, what you do is that you linearize this G tilde with respect to UT, and then you see that there are two terms that pop out. The first term is basically how a machine learning model is trained. It's trained to predict the next time step with the model and match it against the true state at the next time step, which is given by the true operator at UT. So this is the generalization error. But as you realize that in these models, it's not just the generalization error of the model, but another term that plays a role, which is the Jacobian amplification. So this is where autoregressive models have something different from regular machine learning based prediction models, is that there is this Jacobian, at least in the first order, that can either amplify or de-amplify your errors. So this is traditional Jacobian amplification that you'd see in PDE systems. This is generalization error. And then if you want to autoregressively roll this out, it turns into a very complicated product of these Jacobians, and then also just the generalization error. So what does that mean? It means that I can look at this term, I can look at the Jacobian and its eigenvalues and be able to say how quickly the error would grow between two models whose generalization errors are the same. So if there are two very big models that have been trained really well by very smart engineers, it's very likely that the errors of those two models are going to be the same. But the Jacobian analysis allows us to say things about how quickly the error would grow in one model as compared to the other. And the way this is done is just by looking at the eigenvalues of this Jacobian. So when we train these models with one large neural network on the right hand side, we had no control over these Jacobians. It's basically whatever the derivative of the neural network with respect to the state. But when we train these models with an integration constraint, with a smoothing kernel, just by virtue of writing it out as ut plus delta t times something, you have a much more fine-grained control over the Jacobian. It now decomposes into an identity matrix plus a number plus a matrix with a very small quantity multiplied with it. So delta t being very small, something that you control, you can make these eigenvalues as close to 1 as you can. And an example of this on a 1D system is that if you control this with RK4 type smoothing kernel, your error would grow very slowly, while if you don't smooth it out, your error might grow very quickly because you have a very large eigenvalue. A large eigenvalue means an eigenvalue more than 1, which is responsible for an error growth that is sort of uncontrollable. But then if you have this kind of a structure, all your eigenvalues are close to 1 and clustered near here. So you have neutral-like stability, and that's why your error grows more slowly. Now, based on that, you can guess, I can just take a black box deep neural network, compute J, and whosever eigenvalue is more, largest eigenvalue is more, would be a worse model. It would have error that grows more quickly. And we wanted to test this out on a simple system, 1D system where we can compute eigenvalues. But then we looked at, we looked at 40 different types of models, different loss functions, different training strategies, different integration schemes, different architectures. The claim is that it's independent of all of it. It should be independent of all of it if it's a scientific theory. It shouldn't be dependent on each of these things. And what we realize is that any of these direct step models where we replace the entire right-hand side with a large neural net is going to blow up pretty quickly, or its error growth would be much larger, while all the other 38 models would have basically the same behavior no matter how you train it. It's because you're able to control the eigenvalues with that identity plus setting. And then I'll skip over this a little bit because it's a bunch of mathematical derivations. What you can do from here is you chew on this math a little bit more, and you realize that a linear scaling law evolves in which you can put any models or a set of models that you want to compare on a big sort of thermodynamic phase chart, where you're basically plotting the next time step error versus the largest eigenvalues times error. And what you're looking at are all the models plotted on this graph. The ones that are neutrally stable would always follow this straight line equation with a slope of 2, and that slope of 2 can be derived by chewing on the math in the previous slide. But more importantly, any model that is on the bottom left is a better model as compared to a model on the top right. So for example, these two models that deviate from the scaling law are basically models that do not have any constraints and hence have uncontrollable eigenvalues. Now, this is the careful point. I have to carefully mention something, that you can end up training a model where even without a constraint, these eigenvalues are much smaller. But the goal here is that you don't, or rather the point here is that you don't have any control over it. You try all your bag of tricks for training large models, and you hope that you can control that eigenvalue. But over here, you can control the eigenvalue by changing delta t. And more importantly, you don't even have to do the computation. You can simply take the Jacobian that you have sort of from backpropagation, take the mean of its trace, and that's a very good estimate of its eigenvalue because of the structure. So essentially, any two models can now be diagnosed in terms of their quality based on a plot like this. And that gives us some intuition as to why these structures work. It works because these models conform to linear stability for short term, And at long term, something else happens, but that's for a different day. But at least for short term error growth, which also determines how you behave in long term, you can't have a model whose error growth is so large in the beginning and then it would magically rectify itself. If it goes off trajectory in the beginning so much, you're probably going to end up with a very poor model. But generally, anyone with a small eigenvalue is going to be a better model. Any of these models with very large eigenvalues is going to be a worse model, and that gives us a diagnosable way to look at different kinds of large autoregressive models without the traditional lens of interpretability, where you look at saliencies and sensitivities and so on and so forth. Something a little more grounded in numerical methods and linear stability analysis. Okay, so I'm going to stop over here and open the floor up for questions because I'm at 8:50.
Wow, fantastic. Thanks, Ashish. Covered a lot there. So thank you very much. Feel free to drop your questions into the chat and I will get to those as they come in. So yeah, don't be shy. Feel free to ask questions. So I love the way that you look at this through this theoretical lens. I think it's refreshing because I think it's often a case with these ML models that, and this has been the case in a lot of machine learning work that it's empiricism and well deep networks work and overparameterization gets us out of some of the holes we find ourselves with limited data. But you mentioned about distilling some of the insights, and you talked about a bit about this at the end. I'm wondering, particularly with respect to your first piece of work where you were able to treat it's a bit like a reparameterization trick, right? You learn the theta in the RK4 rather than the step explicitly. But does that tell us something? Can we learn something from that about the atmosphere, about the system we're trying to model? Does it tell us about energy cascades through the atmosphere? Having learned that, trained that on, okay, maybe we learned something about error 5, but if in principle we were to apply that to observational data, does it tell us something about the atmosphere?
I at least at the top of my head, I wouldn't think so. I think it doesn't tell us anything about the system. I think when I was thinking about it, it was more about if what happens in the model that does not correspond to what happens in the system. So that's how I was looking at it. So that's how I was looking at it.
Yeah, right.
So I know what happens in the system. So the whole premise was that I'm not trying to learn anything new about the system, but I see where you're coming from. Is there something scientifically new that we can gain by having these models? And my answer to that would be not that I can see. Maybe through some of these forced response experiments, there might be something that we find. But this was more about, okay, I know what the system is supposed to do. I want to understand why my model behaves in a weird way. And that was the premise behind this theoretical analysis, is that this model that we have is a dynamical system. So we should treat it that way. This machine learning model is a dynamical system. So everything that holds true for error 5, that holds true for a climate model, the analysis that holds true for a climate model should hold true for this machine learning model as well. So we wanted to do that kind of theory. Let's see how much of dynamical systems theory is applicable to machine learning, and not necessarily the other way around. The other way around is where we started from. Yeah.
That makes sense. But it would equally apply to other systems as well. Presumably, people have started thinking about modeling the ocean in this way, and presumably similar.
Right.
Yeah, similar reasoning would apply.
And like there's I guess amazing work from NYU, right? Lozano's group has done this with the ocean. We have done some of this for high resolution regional ocean. Same sort of principles work out pretty well so far. This little trick of just adjusting the residue with a smoothing kernel. It's something that we have done for years, right? Like it's not new.
Sure.
Like the first 2018 paper that Peter Dubin wrote didn't do this during training, but during inference they did the same thing. And I think this is why it works. It works because it induces stability. Either you can control it, or you were lucky that you had controlled it. Either of the two cases, but that's why it works. Yeah.
Okay. Oh, that's neat. So I mean, thinking then about these experiments that you ran, trying to kind of push Lucy a little bit out of distribution and understand like its response. Um, I wasn't entirely clear, sorry, on the training aspect of that. So you trained it on just a few years of like pre-industrial or like through the 1970s or something, and then tested out of distribution, or how did you train it?
Yes, we trained it on 1980 to 1990.
Okay.
We tested it out between 2010 and 2020. Those were with the observed CO2 runs that we were doing. For
Yeah.
for for the for the biased runs, or like for the 2.5 times CO2 runs, it was just trained on 1980 to 1990, and
Huh?
then we start and then we can start from anywhere, right? Because we don't actually know what the answer is for 2.5 times CO2 anyway. So
Sure.
there's still a lot of problems with that. Like, for example, the SST bias experiments. I guess this is the problem with, or was a problem with other AI emulators as well, that you get this unphysical land response.
Mm,
You have a cooling over land, and this happens because you when you train the model, you showed it the true SSTs, but you evolved the T2Ms. But now suddenly your SST has increased, your T2M is deviating. It has never seen that before, so it can't reconcile.
doesn't know how
So
to, yeah. I was going to ask about that because the ACE2 team, they found, again, empirically, right, that they struggled to train, sorry, to extrapolate having trained on both CO2 and SST. And so actually now they just train on SST, and it's kind of CO2 comes in separately. But is that something you found? Have you tried that? Did it
yeah,
make much difference?
yeah, we're for following exactly the same strategy as that of the ACE2 team. So to kind of do a side by side comparison, when we turn on CO2, just do this on SST. Um, uh, by prescribed SSTs during training, and then during
Yeah,
inference we add a plus 2k bias, but that bias this time, when we add it, we smudge it around the coasts so that there's not a sudden change between the land and the sea surface temperature. So that's what kind of fixes our the weird land response that we were getting, and I guess other AI emulators also have. But that
it
also tells
otherwise
us,
looks pretty good, right? I mean, you do get the Arctic amplification, you get,
yep,
some of the
we
key
do, yeah.
features.
We do get the key features with just that trick, really. But I think there's more that we can do to get this the right way. I mean, we know where it comes from, right? The temperature deviate, the evolution, the T2M evolution deviates from the truth, and SST is correlated with the true T2M. So
Yeah.
really, we are incurring a bias, so we need to correct that bias. So
Yeah.
I'm sure we can do that over time. But still, this is promising that perhaps we can do out of distribution experiments up to a certain extent.
Yeah, yeah. No, it's pretty impressive how far you can push it, really. And I guess part of that maybe is due to the simplicity of the model, right? It makes it easier to extrapolate in some sense.
Probably,
Um,
yes.
Speaking to that, do again, I don't know. I find myself maybe thinking too much about it, but like, what does so the fact you can model the climate with a pretty small model, right? Pretty simple setup. Um, does that tell us something about, the climate system? Is there some inherent lower dimensionality?
Right. So, okay, this is an interesting point, and this actually ties back to some of the theoretical work that we are doing. And previous to Lucy 2D, so Lucy 2D is a version where you have just a few prognostic variables, right? And you didn't do any CO2 experiments, but you're able to run it stably for 100 years.
Yeah,
So so that this is like saying that I am modeling a dynamical system with only partial observations. So
yeah,
when you model a dynamical system with partial observations, you need a closure term, right? That's the whole idea. If you do not know that's the fundamental of turbulence. So we do not have an explicit closure term. So where is that closure term coming from? And my understanding is that this closure term is coming from some sort of an implicit coarse graining that's happening. And
Yeah.
in this work, theoretical work that we're doing, we expand out these errors. And when we do, when we write out the math, we realize that this Jacobian amplification term that you see, and this Jacobian amplification term is not just a thing that appears for integration constraint models. It's there for all models. In the integration constraint models, we can see it explicitly because we write it that way. So this Jacobian amplification term is actually a restoring force. So if you observe the eigenvectors and the eigenvalues for a simple system, you'd see that generalization error is what takes you OD. The Jacobian amplification, because of its negative eigenvalues, act as a restoring force, which is like an implicit closure that is, that may be correcting your model. Otherwise, there's no reason to believe that I can evolve the atmosphere with 4 variables over 100 years. And this is not the only paper. There was a paper right before this, you probably know, and I cannot remember the name of the first author. But they also showed that you can do very low dimensional long-term modeling. So empirically, yeah, but I think the underlying reason could be that there's a low-dimensional manifold that everything can be projected on, or I think a more easier reasoning is that there is somewhere a closure term coming out of this model that we do not explicitly see, which is correcting this.
That's cool. Yeah, I need to think about that. Thank you. We did have a question coming. I think we're out of time. I think we have to leave it there. But feel free to follow up with Ashish offline afterwards. I'm sure we'll be happy to answer any questions. Thank you again for the great talk, Ashish. Really appreciate your time.
Thank you,
and we will see everyone. I should have checked, but I think we are here in 2 weeks' time, on the 17th of November, for another climate science AI talk. Thank you very much. Thanks,
Thank you so
Ashish.
much. Thank you.
Bye, everyone.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.